Hello, this is Dr. Keith Schubert. This will be a video lecture on solving inverse Laplace transforms by doing partial fraction expansion. I'll first show you the way that the book does it, and then I'm going to show you what I think is a much easier way of doing it. So we'll do this by an example, and we'll just pick a fairly simple one. We'll take 1 over s times s plus 1 quantity squared. And what we want to do, if we're doing it book fashion, the book expands it into 3 terms: a1 over s plus 1 quantity squared, and then an a2 over s plus 1, and then an a3 over s. And then what they do is we'll solve first for a1 and a3 because those are the easy ones to get. To get a1, we're going to multiply both sides by s plus 1. So that's the first thing we'll do. Leave a little bit of room on yours when you're writing it, because I have to put the evaluate at point. But first we'll do this, a1, and then we get a2 times s plus 1, because we're multiplying by a squared, so it cancels the bottom. And then we get a3 times s plus 1 quantity squared over s. And then we'll evaluate each one at s is equal to, in this case, -1, because we want it so that it will cancel these out. Doesn't matter there, here, evaluate at -1, here we evaluate at -1. When we evaluate this at -1, this goes to 0, so it disappears. Evaluate this at -1, that goes to 0, it disappears. Evaluate this one, we discover that a1 is equal to -1. And we are happy with that, and that's nice and easy. Now the second one we do is take this same lovely expression, and we're now going to get a3, so we multiply through by s. So first things first, multiply on the left hand side, we get s plus 1 quantity squared, and then on the right we get a1 s over s plus 1 quantity squared, and a2 s over s plus 1 plus a3 over s times s, and the s's cancel, so we just get a3. Now when we evaluate this at s equals 0, the root we just got rid of, so we evaluate it at 0, 0, 0. So when we do this, what we end up with is on this side we get a 1, and then this is a 0 on top, everything else is constant, so that goes to 0. This one has an s on top, s plus 1 on the bottom, so it's a 0 over 1. Again, it goes away, and this is just a3. And that's nice. Now we figure out, what do we do with this? And that's where we struggle into our little problem. So now we are going to have some trouble if we just try to do the multiply through check. So what we're going to do, since we notice these are powers, we're going to actually multiply through by s plus 1 squared again. Again, leave a little bit of room because I got to do a bunch of stuff on this one. So I get 1 plus s on the left. I end up with a1 for the first term. And I end up with a2 times s plus 1. And then I end up with my a3 times s plus 1 quantity squared. I'm just going to write it times s to the -1. What I'm going to do is now I'm going to take the derivative with respect to s of both sides. Now the second I do that, this term goes away. I take the derivative of constant, goes to 0. When I take the derivative of this term, I've got derivative of constant, no worries, so I take the derivative here. The derivative of this is just 1. So it's 1 times a2. So I end up with a2 now, first term that comes through. And then I take the derivative of this, and I'm going to get 2 times s plus 1 times s inverse, plus, and I'll get a minus s plus 1 squared times s to the -2. And so I get a3 times 2 s plus 1 S inverse, and then minus 1 times S plus 1, or S to the minus 2. And this is just the product rule. So now I've got the derivatives of both these sides. And then I'm going to evaluate, so the derivative of this one is just 1 over S squared minus. All right. So that's the derivative of the left. And then we're going to evaluate this at S equals minus 1, the root that we're interested in. Now when I do that, I'm going to end up over here. This is just minus 1. And the A1's gone, the A2 remains, but here's the fun part. The minus 1 comes in here, and this is a whole bunch of stuff times 0, and then stuff times 0. So this whole thing just goes away, and I'm left with that. That's cute and clever, actually. Works out well. It is the correct answer. Now, the question is there a different way to get this? Because if this was fairly complicated, I mean, I deliberately, picked a nice example with clean numbers and everything like that. So everything worked out very nicely. What would you do if that were not the case? So let me put on a blank sheet of paper, and we'll do this same problem again in the one that I think personally works out nicer. Now, it's not particularly what I would say is nicer for a human being. It's nicer, as I would say it, because I can do this on a computer. And that's really what I'm aiming for when I'm solving these problems. So now what I'm going to do is I'm going to write this as a thing of, let's say, actually I'd use A's there. Let me do B's here. So I'm going to do B1S plus B2 all over S plus 1 quantity squared, and then I get plus B3 over S. Now, this is the way I am writing mine. The reason why I write mine this way is because it's just fairly easy. Now, I could have written it exactly their way and still done this same technique, and I'll show you that on a third sheet of paper here. But let me just show you how this works out. What I'm going to do now is just multiply through by the denominator. And what I get is 1 is equal to, when I multiply through, it clears out the S plus 1 squared. So I end up with B1S plus B2. And then this whole thing times an S. And then this one gets multiplied by the denominator. So I get plus B3 times S plus 1 quantity squared. Now, when I do this, I find out that I have, let's gather together, we'll distribute this and then gather together. So I get B1, this is S squared plus 2S plus 1, so the S squared term gives me B1 plus B3 times my S squared. So the B1 from here and the B3 from here. And then I get a B2 times S. And again, the S term from here, S plus 1 quantity squared, is S squared plus 2S. So I get a 2S times B3. So plus 2B3 times S. And then there's no other just constant terms, but this one has a 1 times B3 plus B3. You might be looking at this and saying, oh, this is not easier. But watch. I now equate powers of S. There's no S squares on this side, so I have 0 is equal to B1 plus B3. I have S's, there's no S's over here, so 0 must be equal to B2 plus 2B3. And then I've got 1 equals B3. So this is a fairly simple set of equations. Now, if they were complicated, I've got this nicely in a form where I could solve this using MATLAB, or whatever your favorite solver is, because I would just convert this in here. This is my B column. So if I find out 0, 0, 1 is equal to, and then I've got this, and my unknowns are the b's. 2b3, wouldn't it figure? Nobody ever calls, and now I try to record some videos and everybody in the world wants to call. Okay, so the first row is handled by the first equations, b1 and b3, no b2s. Second equation has a b2 and two b3s, but no b1s, and the final one only has b3s. So I could take this and set it into MATLAB and just, say, classical b equals ax, and then my answer x is just equal to a\b using MATLAB notation. That's very easy to do. Now, since this happens to be upper triangular, there is a really easy solution using back substitution. And since I've got this 0 here, actually it's parallel even. So you could almost not ask for a nicer equation than this. So I've already got b3 equals 1, and I can look in here and I can find out from this. I take b3 to the other side, which is just 1, so b1 must be equal to -1. And then I've got my b2 right here. I take -2, so b has to be equal, or sorry, b2 has to be equal to -2. Sticking them in that equation. Now, everybody might be going, oh, wait. What's the problem here? I did not get, I had 1, -1 before. Yeah, but you had a slightly different equation. And this is what I was going to show you here. To get this into the form that we had before, do I have enough room? I think I might have enough room. All right, we have at the moment b1 times s plus b2. So that becomes b1 is equal to minus s, right? Because it's b1 is -1, so it's minus s, and b2 is -2. So it's minus s minus 2. Now that's the top up here. Now what we want, though, is not this form if you're going to do the comparison. To do the comparison, we have this. Right? So to get between these two, I have to be able to combine these two terms, which means I have to multiply by s plus 1 on both of these. So that means I have technically my b1s plus b2 has to be a1 plus a2 times s plus 1, because that gives me my common denominator. The a3 and b3 are clearly equal to each other, and indeed we got the same value for them, so that's no problems. But to get the combination of these two, a1 plus a2 times s plus 1, so the denominators are the same, must be equal to this. So that means this has to be equal to a1 plus a2 times s plus 1. And I got this for my b's. Now let's pull in my a 1s and 2s. Well, we found a1 was equal to -1 and a2 was equal to -1. So that's -1 plus -1 times s plus 1. And -1 times s plus 1 gives me minus s minus 1 minus another 1, s minus 2. So you get the exact same values. And as a matter of fact, you could use this top equation to convert between them. You'll in particular notice that my a2 over here corresponds to b1. So it's the one that ends up multiplying the s. And then the a1, right, what I actually end up with is a1 plus a2 has to equal B2. So when I solve for my B2 over here, since A2 is B1, I could use both of these equations to get a converting equation, and I can find out that A1 plus B1 has to equal B2, which means A1 is equal to B2 minus B1. And B2 is minus 2. And B1 is a minus 1, so it's a minus 1 or plus 1, which gives you a minus 1. So that means A1 has to equal minus 1, which indeed it does. So I just do that to show you that both ways do work the same. This way is fairly decent for a human being to kind of quickly check things because it removes the need for you to do any algebraic solving. That's a big bonus if you're stuck on a test and you got to do things by hand. This one is really great if you are in real life trying to solve a problem and you have access to a computer, because then you let the computer solve it by you get the equations here, equate powers, stick it in MATLAB, and let MATLAB do your work. Either way, you are able to then clear things up. So it doesn't matter which one of these two I pick at this instant. Both of them will do the same thing for me. So I will just pick one of them. I'll stick with the one we did first as we go on, just for simplicity. What that means is that 1 over s times s plus 1 quantity squared is equal to, a1 is minus 1, so I have minus 1 over s plus 1 quantity squared. And a2 we found was also a minus 1, plus minus 1 over s plus 1, and a3 is 1. So this partial fraction expansion has just gotten us a simpler expression. That's all it does for us. Now, the reason why we went to the work to do that was because then we could look these up in our tables. And if you look these up in your tables, you will discover that we have inside the table the expression for 1 over s plus a. And it maps back and forth between e to the minus at times u of t, the step function. So that is this term right here. So using that one, we just have a is equal to 1 in this, and the minus 1 multiplies both linearity, so we end up with a term that this function we are trying to solve for here in time, right, if that's capital F of s, this is little f, right, our second term has to be minus e to the minus t u of t. That's that second term right here. Now, the first term is very similar to it. You can look up the property and we'll see that t times e to the minus at u of t, Laplace transform, gives us 1 over s plus a quantity squared. If you don't have this one in here, you'll actually notice this sometimes as just t times f of t, and it just gives you the square of the one. But in any case, by looking at this one, we can say, there we go again, and now we again have a equals 1. So we can just take this first term and bring it down, and we get t e to the minus a, and a is 1, so e to the minus t times u of t. So that gives us our first one. The last one is readily available also in our tables. You will find that our step function u of t goes to 1 over s. So you will find that we then have here plus u of t. And so that gives us our inverse Laplace transform of the original expression up here. That's what it is equal to. Now, if you watch this one right here tells you, since I've got a t times e to the minus t u of t and then e to the minus t, this is a critically damped response of a second order system. It's third order because I gave it a step input. So this you can kind of consider your initial, transient response to a boom, and then this is the actual, this is the forced one, and then this is the system's characteristic. So we've got the homogeneous in particular, or characteristic in particular, depending on whichever way you like to say it. So in any case, you can see the critically damped nature of it, and you could also get by the repeated root up there. And that gives you a way of handling inverse Laplace transforms two different ways, book way and my computer compatible way. Hope it helps. See you on Tuesday.